DF-41 Dongfeng-41 China's Road Mobile Intercontinental Ballistic Missile. The evolution of mobile nuclear deterrence in the modern era of strategic weapons engineering. Survivability has become just as important as destructive capability. Nations that rely on nuclear deterrence must ensure that their weapons cannot be destroyed in a first strike. The solution to this challenge has driven decades of innovation in missile design, launch systems, and deployment strategies. One of the most sophisticated results of this evolution is the DF-41, also known as Dongfeng-41, China's most advanced intercontinental ballistic missile. Unlike traditional silo-based missiles that remain fixed in underground launch facilities, the DF-41 represents a new generation of road mobile strategic weapons. Mounted on massive transporter-erector-launcher vehicles capable of moving across large geographic regions, this missile can relocate continuously, making detection and targeting extremely difficult. First publicly displayed during military parades in Beijing and widely believed to have entered operational service around 2017, the DF-41 is designed to strike targets on any continent on Earth, with an estimated range exceeding 12,000 to 15,000 kilometers. But the DF-41 is more than simply a long-range missile. It represents a complex integration of advanced rocket propulsion, autonomous guidance systems, MIRV warhead technology, and highly mobile launch platforms. Understanding this system requires exploring the science of missile engineering, strategic mobility, and orbital trajectory physics. Chapter 1: The strategic logic behind mobile ICBM. Traditional intercontinental ballistic missiles were deployed in hardened underground silos during the Cold War. These facilities were designed to withstand shockwaves from nearby nuclear detonations while protecting missiles from sabotage or conventional attack. However, fixed silos possess a fundamental weakness: their locations are known to adversaries. Advances in satellite surveillance and reconnaissance technologies mean that silo coordinates can be precisely mapped and targeted. To overcome this vulnerability, engineers and military strategists developed mobile missile systems. These systems place ICBM on large transporter vehicles capable of moving along road networks, tunnels, forests, or remote terrain. The DF-41 represents one of the most sophisticated implementations of this concept. Mobility dramatically increases the survivability of strategic missiles by creating uncertainty for potential adversaries. A missile that can relocate hundreds of kilometers between surveillance passes becomes exponentially harder to locate and destroy. This concept is often referred to in military strategy as second strike survivability. A credible second strike capability ensures that even after absorbing a surprise attack, a nation retains enough weapons to retaliate. This balance forms the core of nuclear deterrence theory. Chapter 2: Engineering the DF-41 Missile System. The DF-41 is among the most technologically advanced intercontinental ballistic missiles currently deployed. Estimated specifications include length, approximately 21-23 meters, diameter, roughly 2.25 meters, launch weight, about 80 metric tons, although significantly lighter than the massive RS-28 Sarmat. The DF-41 compensates through advanced propulsion and compact payload engineering. One of the defining characteristics of the missile is its three-stage solid-fuel rocket design. Solid propellant rockets have several advantages for mobile missile systems: faster launch readiness, simpler maintenance, safer transportation, long-term storage capability. Unlike liquid-fueled missiles that must be filled shortly before launch, solid rocket motors contain propellant already cast into the engine casing. This allows mobile launch vehicles to fire within minutes of receiving launch commands. Chapter 3: Solid rocket propulsion. Physics. The propulsion system of the DF-41 relies on high-energy composite solid propellants. These propellants typically consist of three main components: oxidizer crystals such as ammonium perchlorate, powdered aluminum fuel particles, polymer binder acting as both structural matrix and combustible material. When ignited, these materials undergo rapid combustion, generating extremely hot gas expanding through the rocket nozzle. The thrust produced by a rocket engine can be described by the fundamental rocket thrust equation: F equals V plus P minus pi E, where F equals thrust, M equals mass flow rate of exhaust gases, V equals exhaust velocity, P equals pressure at nozzle exit, pi equals ambient atmospheric pressure, A equals nozzle exit area. In solid rocket motors, the propellant burns along carefully engineered internal surfaces known as grain geometries. The shape of the propellant grain determines how the burn surface evolves during combustion, controlling the thrust profile of the rocket. For long-range missiles like the DF-41, engineers design grain shapes that provide powerful thrust during the boost phase while maintaining stable combustion throughout the burn cycle. Chapter 4 Transporter-erector-launcher TEL systems. Perhaps the most visually striking component of the DF-41 system is its transporter-erector-launcher vehicle. These massive vehicles carry the missile horizontally during transportation and then raise it vertically before launch. The TEL platform used by the DF-41 is believed to feature an 8-axle heavy transporter capable of carrying loads exceeding 100 tons. The vehicle performs 3 primary functions: transportation across road networks, hydraulic erection of the missile to vertical launch position, launch stabilization during firing. Hydraulic actuators raise the missile from horizontal to vertical orientation in a carefully controlled motion. The vehicle's stabilizing legs then extend to distribute weight evenly across the ground. These stabilization systems prevent tipping or structural stress during ignition. Chapter 5 MIRV warhead technology. A defining feature of the DF-41 is its ability to carry multiple independently targetable re-entry vehicles, commonly known as MIRV. Instead of delivering a single warhead, the missile carries multiple nuclear payloads that separate during the mid-course phase of flight. Estimates suggest the DF-41 can carry up to 10 MIRV warheads depending on payload configuration. After the missile completes its boost phase and exits Earth's atmosphere, the payload section known as the post-boost vehicle begins deploying individual warheads. Small thrusters on the post-boost vehicle perform precise orbital adjustments, aligning each warhead with its designated target trajectory. Each re-entry vehicle then separates and continues toward Earth independently. This capability dramatically increases the strategic effectiveness of a single missile launch. Chapter 6 Intercontinental range and trajectory mechanics. The DF-41 is designed to travel distances exceeding 12,000 kilometers, placing nearly every region of the globe within potential range. The missile achieves this range by entering a suborbital ballistic trajectory. Unlike satellites that remain in continuous orbit around Earth, ballistic missiles follow a path that resembles a portion of an ellipse. The maximum altitude reached during flight is known as the apogee, which can exceed 1,200 kilometers for intercontinental missiles. During the mid-course phase, the missile and its warheads travel through the vacuum of space at velocities approaching 7 kilometers per second. At these speeds, a warhead launched from Asia could reach targets in North America within roughly 30 minutes. The trajectory calculations required for this flight path are performed by sophisticated onboard guidance computers. These systems account for factors such as Earth's rotation, gravitational perturbations, atmospheric drag during re-entry, precise target coordinates. Chapter 7 Inertial guidance and navigation systems. Unlike aircraft that rely on GPS signals for navigation, strategic missiles use inertial navigation systems. These systems operate entirely independently of external signals, making them immune to electronic jamming or satellite disruption. An inertial navigation system measures motion using 3 primary components: accelerometers, gyroscopes. Onboard flight computers. Accelerometers measure linear acceleration along multiple axes, while gyroscopes track rotational motion. By continuously integrating acceleration data over time, the system calculates velocity and position relative to the missile's launch coordinates. Modern systems often incorporate ring laser gyroscopes or fiber optic gyroscopes, which use the interference patterns of light traveling through rotating optical loops to measure angular velocity with extreme precision. These technologies allow the missile to maintain accurate targeting across thousands of kilometers. Chapter 8 Re-entry physics and thermal protection. As the warheads from the DF-41 descend back toward Earth, they encounter the extreme environment of hypersonic atmospheric re-entry. At speeds exceeding Mach 20, air molecules in front of the re-entry vehicle compress violently, producing temperatures exceeding 7,000 degrees Celsius. To survive this environment, warheads are protected by ablative heat shields. These materials absorb heat by slowly vaporizing and carrying thermal energy away from the vehicle's structure. The resulting plasma envelope surrounding the warhead can briefly block radio signals and radar detection. This phenomenon is known as plasma blackout. Despite these conditions, the re-entry vehicle must maintain aerodynamic stability while descending toward its target. Engineers designed the warhead's conical shape to balance drag forces, heat distribution, and stability during hypersonic flight. Closing narration. Mobility and the future of strategic weapons. The DF-41 represents a powerful example of how modern military engineering combines mobility, precision guidance, and advanced rocket propulsion. Its road-mobile deployment strategy dramatically increases survivability, while MIRV technology multiplies its potential strategic impact. As aerospace technology continues evolving, the line between missile engineering, spaceflight physics, and advanced materials science grows increasingly blurred. Yet the existence of such weapons reflects not only technological capability, but also the fragile balance of global deterrence that has shaped international security for decades. Understanding systems like the DF-41 reveals not just how these missiles work, but also how science, engineering, and geopolitics intersect in the modern world.